Hi, I'm Yehuda Ben-Shimol, Ben-Gurion University, the Communication System Department, and I will present ray tracing with Mathematica. Hello, I'm Yehuda Ben-Shimol from Ben-Gurion University. I will try to describe a track of development for ray tracing of electromagnetic waves in Mathematica. It sounds not so rational to do it, but I will describe what happened in a way. So we have a scenario about, let's say it's a city, or part of a city. This is a real city, but I cannot say what it is because of the application behind. And in this pink area, there are several, let's say, cellular telephones transmitting and using, let's say, flying elements above the city, far behind. We want to track what is the position of each transmitter in high accuracy. And you are in a passive mode of receiving the radio wave. So actually, if we look, the pink area is a region of interest. Now for the experiment, we know where are the transmitters. And for other models, you need only the 2D layout of the buildings. You need the height just for some parameters, but actually you need some uncertainty area, like the purple one, and the orange one is really the area of interest. So we started with the models that we developed, a colleague of mine and I. And this model is a stochastic model. Let's say in an average city, with such and such distribution of buildings and parameters like what is a line density of the buildings, what is the distance between the transmitter and the receiver, the profile of the height of the building and the height of the transmitting antenna and the receiving antenna, lots of assumptions. But in, let's say, in conventional cellular applications like mobile telephones and antennas above the roofs or in some tower of 20, 30 meters, it's quite accurate. We've made experiments with some cities in Europe and it was okay. Another advantage of this model that you can have even a Doppler to calculate the Doppler shift that is received by the receiver antenna. And actually, what we were asked to do is to check this model with, let's say, a mobile receiving antenna, three of them, because we have to do triangulation, and to try to locate where are the transmitters. Okay, so we had a lot of information. We did it with Mathematica, this model, and we had huge amount of information, but actually the comparison was not successful because the type of the measurement, this is a stochastic model, so you need repetitive experiments, and we had only one experiment with lots of data, and we couldn't verify that we actually can do what we were asked to do. So I decided to check the model later with another verification concept, like ray tracing, because ray tracing is highly numerical. You cannot have insights like a theoretical model, but it's accurate for a specific scenario. Okay, each scenario you have to run again. So since we have so much work done with Mathematica, I decided to do it already with Mathematica. So what is ray tracing? Okay, ray tracing is a method, just you mimic the transmitter like a bunch of rays, and the ray propagates. Now they hit walls, they hit boundaries, they hit concrete, some of the energy dissipates. And actually this technique is used in graphics, and nowadays even in cellular telephones they have GPUs, so they used to render the screen, especially in games, with this technique of ray tracing. But we are not doing propagation or ray tracing of light because it behaves differently, because it's not colors. We have the same frequency and it doesn't change color. And actually behind the scene, we want to add to the, let's say, the buildings, lots of parameters like how many metal inside the building, how many windows, where are the windows, where are the corners, and lots of parameters are very important, let's say, for electromagnetics, but it's not important for optics. So we needed some advanced tool to do this. So the theory behind the ray tracing will not explain the equations. It's only the set of Maxwell equations. Usually, if the frequency is high enough, so the wavelength is small enough according to comparing to the buildings, and this is accurate enough. So let's say we work with 30 centimeters and below wavelengths, and the buildings are at least several meters. Most of the buildings were 10 or 15 meters height, so it should be accurate enough. Now I was faced with a problem. I want ray tracing. I want it to be combined with Mathematica, and I want to work as less as possible because I don't have enough time. So I scanned the market, what we can do. So there were several tools on CPU, okay, like POVRay, it's very famous, Blender, Yehuda, many applications that can do it, but they are all for ray tracing of light. And if you want electromagnetics, you have to work hard within the framework to modify it for electromagnetics. There are several tools also for GPU to do it faster. NVIDIA proposed optics, and very simple version of optics is called Optic Prime. It works only with triangles, but you have to feed the GPU with a set of triangles and a set of rays and let it work. It should work very fast, but I don't know C++. And to activate such thing, I need to learn C++, so I decided not to do it. AMD, they have a long-term project also. It calls AMD Radeon Rays. It's very similar to optics, and it's now open source. If anybody is interested in working with AMD GPUs, so you can use it. And actually, for scientific research, it's not enough to have a ray tracer. Ray tracer just give you the path of the rays, but there is lots behind this. So I decided, okay, what the hell? I will do it with Mathematica. So I have a balance to make. Why Mathematica? So lots of import and export. So I got the building from somebody else. So I have to read the buildings in another format. This time it was a file of MATLAB, but Mathematica knows to import this type of files. You have rich libraries for region and geometry to describe the buildings. You have all the mathematical functionality to analyze the results. You have graphical tools, as I shown earlier, just to display the results. And if I want to compare it versus a theoretical model, of course, I have the theoretical model, I have the results. Now I just have to do ray tracing and compare. And I know Mathematica well, so I thought it would be a nice experience to do it. So if make it short, it was a nice program, so I smiled, and it was for me, so it was embarrassing because I don't have enough time, but I did it anyway. So if we look at ray tracer, there are very simple task applications. They have as input many 3D polygons, usually. Most of the time it's triangles, keep it simple and fast. You have a set of rays, like the origin or flashlight for optics or lamp. And you have the position of the viewer, where you want to measure the result. For electrodynamics of waves, it's just an antenna. So you have to describe the antenna and what's the proximity of the antenna considered as a, let's say, received signal. And the task is to compute as fast as possible the passes of the rays. And each time it reflects from a wall, you have to calculate the angle next time and make it like secondary array and say one reflection, double reflection, three reflection, four reflections. Usually everybody does two. We decided to do more. Okay? And if it happens that it hits like the corner of a building or the edge of the building, there are other models that not much, not like what happens in optics, how to calculate the dispersion of the waves around the corner. Okay, so compute as fast as possible. Actually, each ray tracer, to do it as fast as possible, need to do two things fast, okay? And ultra fast is much better than fast because it has lots of computation to do. First of all, if a ray hits a triangle, you have to find this point because in usual scenarios there are many triangles. So you have to do it fast. And you have to compute the direction of the reflected ray. An efficient way to do it is not to try to intersect the ray against all the polygons or against all the triangles. There are many ways of subdividing let's say the buildings or the rays according to spatial partitioning or object partitioning, and you actually try to find where is the building or where is a collection of triangles that you have to do the actual computation in step one. And this is an important step. This is not implemented yet in Mathematica, but I did it without it. Now, let's say how I started. So instead of several years ago, I had two students that developed something similar to in building, not in an urban environment, but inside buildings. It took them on a GPU just to develop the application about 8 months, and they were very proficient programmers on GPU. It was a work of about 7 to 8 months just to get the application. I don't have enough time to do it for so long time, so it took me about 2 weeks to finish everything. So I started with, okay, how can I describe array? So there is an object in Mathematica called half-line. It's like a line that have origin, and then it can be infinite line. So you can describe it like half-line between 2 points or half-line between the origin point and the direction of propagation. This is what I used. Okay, this is very good. Now, how can you find where it intersects with the building? So there is another fantastic function that is called region intersection. So you have to describe the building as a region or as a graphical object and then do the computation. This function is very fascinating, but it is very, very slow. So just to see what happens, if you see the red dots, it's like the position of the transmitters. And usually you have two options. Or you mimic the rays transmitted, but then you have to do lots of rays because you don't know if it's actually get its way to the receiver. Or do the opposite, which is usually what it is done. You do inverse rays. You transmit the rays from the receiver because you know they are there, and you collect only the rays that get near the transmitter, which is more efficient. So we can see what happens here in some scenarios. So first experiment, just use what Mathematica offers. Don't try to do any optimization. So just for an example, just for this demo, so you see I took one ray, one building. Now, just for this case, it's represented as a cuboid. We can see that actually the ray intersects with the building. So we should get an answer for this, but how fast it is. So here is an answer. Do it 10,000 times, which is a small number of repetitive intersection for such an application, took 20 seconds. very, very slow. It should be a fraction of a second. So I decided to do version 2. Okay. The main problem then when I investigated what is the cause, like I needed 1 million rays at least, so it took about 25 hours. So it's not a reasonable time. With a strong computer, Xeon, 8 cores, running Mathematica in parallel, lots of RAM, and actually it took about 25 hours just to get the computation done. Okay, so version 2, it was, okay, let's move to triangles. Why triangle? Because then I can change the function region intersection with another function that doesn't have to compute what is the object. It knows it's a triangle. What is another object? It knows its way, so it just can take the parameters. So there are many options out there. So I took one function that is considered very efficient and modified it to Mathematica. This is all the code, very simple. What we see here is a polygon of 3 points. So it's a triangle. We have a half line. And you can use this. There are several conditions to stop the computation in advance if you know that some condition is not met. So no intersections, there is a symbolic answer, empty region in 3 dimensions, so empty region 3. And finally, if something is correct, so you have to give this, and the parameter t that is computed actually answer, this is the intersection point. Okay. So just another performance measure. Now I have to work with triangles. So I took the objects that describe the building and triangulate it. So by boundary discrete graphics is very good. You can do also discretize the graphics, but it considers the volume. I want only the envelope of the building. So I have 4 walls and the ceiling because some rays can bounce from the building. And actually what happens that I cut the computation time in half. But say, okay, next step, what can we do? These functions that I used is quite simple, so we can compile because all I need is just vertices. But there is another problem, okay? I got almost a factor of 2 performance, but if you look at the code, Mathematica is a symbolic function, so the same function can return different answers. It can return a number, it can return a symbol, it can return a vector, whatever you like. It's like an object. And in compiled version, you cannot do it. It has to be the same type. So the first thing that I have to cope is how to modify this. So I picked the immediate solution. Just use 2 functions. One will return true, false. There is intersection, no intersection. And if I have a true answer, then just compute the intersection. So I created a wrapper function, okay, that gets a symbolic expression. The reason is there was a bunch of code. I didn't want to modify it too much, so I just changed the name of the function and did a wrapper function. And then this wrapper function called to 2 other functions that are compiled. So it should be very quick, okay? So the first one is a Boolean function, true, false. You have intersection, okay? And I compile it to C, which is the fastest option, at least for version 11.1 and 11.2 that we did this project with. And this repeats part of the computation. Actually, I can modify this just to transfer a vector of parameters that were computed with a previous function and even short the computation time. So now, if I repeat it 10,000 times with the same, now I have a set of 2 triangles per wall, which is highly efficient. I don't have small triangles. And actually, I got a factor comparing to the first version of only Mathematica of about 37. Okay, this is very good. And these results are from the laptop. I got better results on the desktop. Okay. Now, now I want to do it better. Okay. So better, it means that I use parallel computation of Mathematica, just run things in parallel, and in parallel I got even better results. Okay. So the best that I can get with this computer is about factor of 60. Here on the small laptop, it's 4 cores. Okay, on my desktop computer is 8 cores and Xeon, so it's better and it doesn't hit. It can compute for a long time and it's okay. So just some results to see it. I took a random sample of rays, like 150 rays just for the presentation, out of several tens of thousands of rays, just to show that it would work. This is like the direct hit. Now a single reflection, a double reflection, a triple reflection. I have another image for quad reflection, but I didn't show it here. And now version 4 was, what I planned is to do GPU, but all my computers are Apple, and Apple decided to abandon OpenCL, and I cannot use CUDA. So I had a problem, so I stopped the project for the time now. Until somebody will decide what Mathematica should do with AMD GPUs. Okay, if not, somebody else will continue to develop it on Windows and Linux. Okay, final comment. I found a page in Wolfram.com actually describing some of the internals, and on these internals, he described what happened with graphics. Okay. And actually, to do graphics with Mathematica, you have all the functionality of ray tracing. Okay, so I hope somebody will pick up the, let's say, the glove, and provide us some interface that we can use as external users to do ray tracing using this functionality, and let us modify it. Okay, this is the last minute comment. What I've seen in this conference with version 12, with all the new compiler capabilities, actually I can do much better than the results that are shown here, so I'm waiting to the next version. So, okay, thank you.